one last piece here for projections. It builds out of, well, we can see it as building out of what we've talked about so far. It could come separately. But the idea is let's project onto a subspace, not column space or null space or anything, but just a subspace for which we have a basis. So someone hands you a subspace of a RM and says, please project vectors onto, please find me the projection operator that will project onto any vector onto that subspace. So I know this is exciting. A couple of pages here. And I'm just going to talk through these things. So we know how to, so that's what this first piece here is. We know how to project a vector B onto a line. So that's actually projecting onto a subspace, a one-dimensional subspace. And so that's been the story here, right? It's a pretty excellent result. We figured out that, in fact, if you just take the vector for which we're, for the line that gives us the direction of the line, doesn't matter what its length is, and in fact, we make it into a unit vector. And then A transpose, right? So it's this outer product, makes an m-dimensional, m by m matrix, which is then a projection operator. So we want to see how we could do this in general. So say we want to project, the plane is here in front of me. We have a vector and we want to project straight down onto it, right? And you can imagine many, many complications. So a bit of a technical piece here, but let's see how it all works. It's very nice mathematically. And then we'll find a thing about the null spaces of A and A transpose A that's quite elegant. Okay. And so it's a useful thing, say we're in 3 dimensions again and so on. It's useful to have these, to be able to build these projection matrices, right? So here's a plane. The idea is we have a plane. We have B, E, we have P lives in the plane, and then E is the error, what we've called an error vector. It's perpendicular, it's normal, in this case, to the plane. Now we're going to talk about it being normal. So say we have this subspace. Yes, it's a plane here, but it could be a 32-dimensional subspace of 83 dimensions, whatever it is. As long as we have, someone hands you a basis, right? We could go through the work to find a basis, which we didn't have to do for the column space problem. And that's an interesting detail, but let's move on. So we've got a basis. It's an R-dimensional subspace of Rm. Therefore, we have R vectors in the basis. And we build something that looks a lot. We make an AX equals B type problem, right? So we're going to say P is some combination of these basis vectors. And that's what X star is, right? So weights. This is the column picture. It's and these are linearly independent because it's a basis. So it looks exactly like AX star equals P from the start. We know these things, right? So we know that we want the this error vector to have nothing to do with the subspace. So it must be at right angles to every basis vector. And we want that we add these two vectors together, we get B, the original B. So did a similar thing before. For column space, the monks say, let's set this problem up like this, A transpose E, right? So that's using the fact that E is in the left null space of this matrix A. We know that E is B minus P, so that's the third criterion. So we're going to separate this out. This would be A transpose B and A transpose P subtracted off. And then we know P is A times X star. We're forcing this projected thing to be only made out of the columns of A, or a basis for the subspace S. Okay. Put that in. That's what this is here. Rearrange, and now we've got the normal equation again. So this is a normal equation, but the A is being constructed from a basis. So we got there, in a separate way. And again, we solve for X star, and then we find this projected thing as AX star. Okay, so here's the difference now that because A's columns are linearly independent. This is the big deal. We can do some things. We can do some other things. We couldn't do for the normal equation in general. So we'll have this in a second. So that so if A's columns are linearly independent, right? They're a basis. You can't make one of these columns out of the others. Another way to say that is the null space of A is 0, right? The only way to combine these vectors linearly to get 0 is to have 0 of each, multiply them all by 0 and add them up. So we can take the normal equation because A transpose A is invertible. Reason is on the next page. Because it's invertible, has an inverse, so we're going to pre-multiply both sides by the inverse. Right, pre-multiply both sides by the inverse. Then this is, right, the whole point was we're undoing this. So we've got, now we've got an identity matrix here, and we've got some blob over here. This is nice. So we're trying to get to this projection story, right? Just as we found for projection onto a line, we were able to build a nice little projection operator back over here, this beast. We'd like to do that in general. Okay, so that's the game. So now we're at x star. This is just the identity times x star, so that is just x star. We've got this blob on the right. And we were all along trying to find the projected version, the projected aspect of P. That is, by definition, A times x star. So we take this blob, multiply it by A. So we've got this funny looking thing now. A, the inverse of A transpose A in the middle, and then A transpose. Kind of a funny looking thing. And if you think about all of the dimensions, they all make sense. So A is m by r. We're living in m dimensions, and it's an r-dimensional subspace. So A transpose is r by m by r. That makes this blob an r by r. And so these things all fit. Maybe I'll make it right. R connects with this r connects with this r, makes it an m by m times an m by 1. So it's all good. So this whole thing, this whole blob, right? This whole blob here becomes this P. It's a big projection operator, right? It's P equals a blob times P. Square matrix. So projection matrix. So this is really a good thing to be able to construct if you're going to be projecting lots of vectors, whatever it is. I know that that's what you want to do in your spare time. Just a little detail here is that if we project a vector onto a subspace or onto a line, for example, and we project it again, nothing should happen, right? So so this is sort of a funny matrix. So P squared should equal P. If you do it twice, it should be the same as doing it once. If you do it 12 times, it should be the same as doing it once. So it's a nice little thing to check. That's what this all says. P to the power of n is equal to P. It's an unusual, it might seem like an unusual thing, right? So that for normal numbers only works for, 1 squared, 1, yeah. So this is an odd thing that matrices can do. Another example of an odd thing that matrices can do. So here's P and P. And what we do is we combine this blob. We've got an A transpose A. And then there's an inverse sitting right next to it. So these things cancel each other out. So here, this becomes an identity. If you sort of look at the structure, you can see why, right? So there's an A transpose at the end of right? There's always an A transpose at the end, and there's an A at the start. So when you multiply two of these together, you construct another A transpose A blob. So this all just disappears because it's just an identity matrix. It just acts like a 1. And we end up with P again. So obviously if we multiply by P again, and P again, and P again, they all get absorbed. So that's kind of cool, right? Okay, so we have this projection operator. This is some nice little bit of thinking here. So we've got a projection operator, it does good things. It might be tempting to do this. This is a bad thing to do. So there's some warnings here. We've got this inverse in here. Right? If you have AB inverse, then that's B inverse, A inverse. if they're both square matrices and everything's good. But A may very well be not, maybe rectangular, not square. So generally we can't do this at all. It's possible, right? So it may be equal sometimes, but generally it's not equal to. All right, so that's a start. We know this beautiful fact that it's always square and symmetric. And then this is just the end of this piece, is to show that when is it invertible? So it's invertible, and we made this claim on the previous slide, the previous page of notes. If and only if, which we ridiculously write as IFF, A's columns are linearly independent, right? So that's true if we start with a basis, that's all good, but let's just, so if we were trying to find, we're using the normal equation on an AX equals B problem, A's columns might not be linearly independent, right? They might not be, like Fezzik, for example, or Inigo, or the Man in Black. They're all examples that fail in that way, or succeed, depending on the way you look at it. Now, this is just, when is A transpose A invertible? Well, A, which could be rectangular, columns have to be linearly independent. If they're linearly independent, that means that A times X equals 0, this is the definition. Right, there's only that, the only way to combine them is to weight them all by 0. There's no way to make one out of the others. Which is the same as saying the null space is 0. And A transpose A is invertible means its null space is 0. So maybe I should add that here too. So these things apply to here, and this is A transpose A's says that the null space of A transpose A is also equal to 0. Right. A transpose A is full rank. And it's a R by R, right? This thing is an R by R. The way we've constructed it here, full rank R. I know, the R's are being repeated a little bit. So we need to show that if one has a null space of 0, in fact, we'll say something more general. The null spaces of these two things are the same. That's this plan here, right? So we're going to show that they have the same null space. So this is very nice. That's how this works, okay? So let's start with 1. We'll assume that X is in the null space of A. So AX equals 0. And then we'll play around with that and show it's also in the null space of A transpose A. So how do we get that? Well, we can just take our equation, pre-multiply by A transpose on both sides, rearrange this so we've regrouped things. So we've got A transpose A on the left times X. This is A transpose times the 0 vector. So A transpose A times X equals 0. So therefore it's in the null space of A transpose A. It's exactly what the definition of null space is. Now, this is a sneakier one. So if we start with X in the null space of A transpose A, then by definition, right, this is definition. That's what it means. So the monks come along and they say, well, you know, you could do something with that. What if we multiplied both by X transpose, both sides by X transpose? All right, so again, we've taken our equation and we're just multiplying both of them by X transpose. Not to be confused with this move. Okay, so take some brackets away. Now we've got X transpose, A transpose here. That's this blob. And then we'll group it with this AX. And of course, this is 0. This is important. On the right-hand side, this is was actually an inner product. So this is a 0. This is just a number. Right? This is just 1 by 1. And you can go through and figure out what all the dimensions are and make sure everything's okay. Our fabulous rule for the transpose of a product is the product of the transposes but reversed. So we can take this blob and rewrite it as a times x. Let me do this, a times x, and the transpose is out here. So now we have something where we have a blob, transpose blob. And whatever that, and they're vectors, right? So this is, it's an, I'm going to clean that up. That's an m by 1 vector. This is m by m by r, and r by 1. Right. Right. So it is an m by 1 vector. This whole thing, let's get that to there. So this is a vector whose inner product with itself, that is its length squared, Pythagoras. And it's a funny looking thing, I think it got moved. So therefore that vector is 0, right? If its length is 0, then it has to be 0. If length is 0, then the vector has to be 0, it's the only vector. So therefore, a times x is equal to 0. X is also in the null space of A. So we started with it being in the null space of A transpose A. This nice little argument, you'll see that versions of this again will appear. So we can do the same thing for A transpose, which will be an important construction for us later on. A transpose A is great, so is A transpose. So the upshot is that if the null space of A is 0, doesn't matter what A is, could be rectangular, fine, right? So it need not be square. A need not be square. Then this matrix, which is square R by R matrix with rank R, it's a great matrix, is invertible. So that's pretty super. It's pretty super. I know you're excited. You should be. It's just a nice thing. And so, you know, when can you make this projection operator? Well, if you've got a basis for the thing it was projecting onto, which you should if you're just working with a subspace, then yes, you can do it. Inverses are nasty. So you're not going to do this for a giant subspace, but for 2x2 subspace, 3x3, 4x4 maybe, and you're something you're using over and over again because it's just what you do in your life, then it's groovy. All right, I think that's good. So that brings us to the end of the. Yeah, let's do it. We can draw on it. We have moved through the dinosaur, right? And we are about here. Now, it's thinner in the neck, but that's partly because you know more things, right? So it's actually kind of fat, which is a weird looking dinosaur. So, you know, the metaphor gets a little strained, but point stands. So because you're smarter, it feels a bit thinner, and then it will hurt a little bit because actually it's bigger. So this is a rescaled difficulty story. All right, but you are here, good. And this is a fun part because you can go whoop, whoop, like that. Okay, all right, team, onwards. I keep saying that, but it's true. Maybe upwards as well, at least along the dinosaur.